Basically, what a buffered system does is it resists changes in pH. They do have max like what's the best way to say this? They're efficient, but you can run a buffered system by overflowing it. All it is an equilibrium thing, just like we saw yesterday, where this salt can then take some of the H's up. And so you're not going to get the pH that you would normally think you would get because it'd be lower. It's going to actually buffer that a little bit, give you a padding on your pH. The best buffer systems, if you're wanting to buffer it well, then you're looking for whatever pH you want. You want that to be the pKa of the acid portion of the buffering system, and then you would want an equivalent amount of the salt. So there we go. Solution that resists changes. Let me go pen real quick. Resist changes in pH. To form these, and I've got some better instructions on the next page to make them. I don't think we're going to go over them because I think if we make buffer next week, then we'll take a look at those. But basically, you have a weak acid and its conjugate base, or a weak base and its conjugate acid, or you can have a salt that has for the acid the anion, and for the base, you can deal with the cations, and we saw how those metallic cations can affect that. So if we take a look, the one we saw yesterday, we had HF and NAF. Here, it should be sodium, not NS. I need to make that correction on there. That should be sodium acetate. So you use acetic acid and sodium acetate, and then a cyanic acid, and then sodium cyanide. These are all decent buffer systems. Now, to take a look at how these work, if we have this right here, we're going to end up having, let's say, just like yesterday, HF plus H2O, and we're going to get that to be H3O plus F negative. Now, if we have F negatives, and we're dealing with our equilibrium, we can see that that is going to basically pick up H's as well as we add more H if we already have an F negative in the system, because we have Na F yielding Na plus and plus the F negative. If we already have this in the system, then it's not going to, either the H's will be picked up by this F negative, or it won't move in that direction as much. But whenever it comes to the OH plus the F, let's do it here. So we have HF in there as well. If we add OH negative, what we're going to get is F negative, and the OH negative is going to be picked up by that H plus, which will then give us H3O plus. So this H3O plus, if that F negative is in there, basically H3O plus plus F negative, that will get picked up. Again, remember that HF is a weak acid, so its equilibrium constant is less than 1. So if all of a sudden you have an influx of this H3O plus, that's going to favor the forward reaction, and the HF will get picked up, and then you will have H2O left over. So basically, these buffered systems pick up hydrogens and put them back into the weak acid, or the weak acid donates a hydrogen to the hydroxide, and you get, oh, why did I do that? I should not have done this. There we go. That weak acid donates its hydrogen to the hydroxide to give it H2O. There we go. HF plus OH, H2O plus. H3O plus F negative yields HF plus HO. So basically through these two mechanisms, we can negate hydroxides, which would change the pH, making it greater, or we can negate hydrogen ions, which would change the pH and make it lower. So we can pull them out to a certain extent and resist the change of in pH. So we already did this. We broke that down and showed you how the Ka is equal to the products concentrations over the reactant concentration. And then we said that we can take and rearrange this equation into the pH plus the pKa plus the log of the base over the acid. Let's see if we can do that. So the first thing we were doing was taking and making the Ka the pKa by taking the negative log of it. And we set that equal to taking the pH by taking, actually, let's do this, negative log. Let's go ahead and do it all the way. See if we can figure out, make sure that we don't fall for the same mistake we did last time. Negative log of the Ka equals the negative log of the hydrogen ion. And then what did we say with this division here? When we do this, Hayden, remind me, or Creedon with the math. We have the negative log of this whenever we want to separate this. We plus the negative log of the,
Yeah,
oh, I can't hear you.
of the thing on the bottom.
Yeah, of the F
Well,
negative
if you're adding, yeah, it'd be F negative, yeah.
and then HF here. And basically that is the, actually I should not put brackets around that. That could upset somebody. Because in chemistry, brackets like that mean concentration. The negative log Ka equals negative log hydrogen ion concentration plus the negative log of the base over the acid concentration. And then we can do a little bit of rearrangement. Negative log of Ka equals pKa equals pH and then we're stuck on this again. I'm trying to think. Is it because this is division? Do you remember? No, the log math. It's minus the negative. See, I need my log, my math, my. And then right here, but this right here, oh, okay, I get it. Yeah, thank you. There we go. So this is adding the negative log. So in reality, if we take this, I see it now. It's just 20 years math ago. So if we take a look here, if we're adding the negative log and we want to rearrange this equation, then we would take this over to here and we get pH equals pKa, since we're adding both sides with the negative log there, plus log of the base, F negative over HF. So it's the switching of the of this from this side to this side. And again, whenever you're looking at these pKas and stuff, I guess I myself also need to take a little better look at what I'm dealing with. But that's the basics of the Henderson-Hasselbalch equation. In reality, you never have to use it, but it's just like that square root of comma. If you get decent at it, it can save you some time. If these two concentrations are the same, then that means that we would have the log of 1. So that means that this would cancel out and the pH would equal the pKa. So that's one thing you can do with the very quickly with the Henderson-Hasselbalch equation. If you're creating a buffer and you want the pH of that buffer to equal the pKa, then you make these concentrations equal. Now the cool thing is let's say that you increase the concentration of the base 10 to 1, but then you would change the factor of the pH by +1. You have more base, so if you were at 7 and you have 10 times as much base as acid, now the pH of that buffer system would be at 8. If instead you had a higher concentration, a 10-fold of the acid to the base, then instead of being up 1, you would be down 1. So that's a way that you can make a buffer system be at the pH that you want. If you dilute this or whatnot, it actually doesn't matter because if it's based on these concentrations ratios. So if you were to add water to that buffered solution or anything, it would not actually change that pH because it's based on their ratio to each other, not the actual concentration of the solution itself. Dun, dun, dun. Again, we will go over this next week and maybe make one, hopefully. Concentration of a buffered solution. Oh, that's what I just said. It's the ratio of the conjugate acid and base. That is important, not their concentrations. So you change the pH, like I said, by changing the ratio. More base is going to increase the pH, less base is going, more acid is going to decrease. All right. So we're going to introduce, we have the ICE table, which you can use with concentrations. There's another table, and sometimes we use this when dealing with just basic stoichiometry and moles. It makes things more organized for acid and base chemistry. So you have the initial number of moles. So in here, instead of concentration, we will get moles. The change as the reaction takes place, and then your after concentration of moles. So over here, hopefully you can see it says basically if there's no reaction and you're dealing with equilibrium, you use the ICE table. If a reaction actually takes place, then you use the BCA table before, change, and after. So if we take a look, the biggest part of this is, yeah, you can also just keep track of it just like this. Before the equivalence point, at the equivalence point, that's for like a titration. But the biggest thing is that moles are in here. And yeah, this is big right here. If you're adding a solution to another solution, the biggest change is going to be in your volume. And that's one of the reasons why we go back to moles on this, because we're not using an equilibrium system where the concentrations are a ratio to each other. We need to do the moles because a lot of times with something like titration, you'll take 25 milliliters of something and add it to 50 milliliters of something. And that's going to now change the volume based on the final volume of that solution being 75 milliliters. So if you have the moles, you can divide by the new volume and find the new concentration. But that's one of the major key factors when doing this. More and more buffer solution stuff. This is exactly what was said. Acid that is added reacts with the base. Base that's added reacts with the acid. And again, this is why this is starred. You need to recalculate the total volume and then the molarity of those two things. Again, let's get the strong ones out of the way. Strong acid base reaction. So if we take a look here, says calculate the pH of a 25 milliliter sample of 0.100 molar HCl following the addition of 10 milliliters of 0.106 molar NaOH. What is the pH change? So it looks like we should probably figure out the pH if we need the pH change for that. How are we going to figure out the pH of this 25 milliliters 0.1 molar solution? What's the easiest way to find a pH of a solution? Negative log, right? In this case, negative log of 0.100. Why can I do that? Because this is a what type of acid? HCl.
Monoprotic.
But more importantly, strong, right? It is monoprotic, you are correct on that, but more importantly, strong. So if it's 0.1, we take the negative log of that, we're going to get a pH of 1, right? You could also look at that as 1 times 10 to the negative first. The negative log of that is 1. So it then says we have the addition of 10 milliliters of 0.106 molar sodium hydroxide. So if we take HCl and we add to it NaOH, that's going to yield HOH, which is H2O, and NaCl. Since HCl is a strong acid, the amount of this is not really going to matter that much. The amount of this is not really going to matter that much. If we have more hydrogen ions at the end, then it will be acidic. If we have more hydroxide ions at the end, it will be basic. Why doesn't this play a factor? Because again, HCl is a strong acid, so it ionizes completely. There's no chance that this salt right here will pick back up hydrogen ions or something like that, like we do with the weak acid conjugate base example. So remember, we need to find the moles for this. So we take, I'll go ahead and write it out just to make sure we're on the same page. 0.025 liters. Basically just change that to liters. Every 1 liter of this is 0.100 moles. So, and we use this one, I think, almost throughout this whole thing, and that is 0.0025. And for the sodium hydroxide, 0.01 times 0.106. So that's going to add another 0 there, 0.00106. So which of these do we have the least amount of? Which one's last? 0.0025 or 0.00106? They're not negative numbers. So which one is closer to 0?
00106.
There we go. Yeah. A lot of teachers are absent right now. So if we take a look, basically what this BCA table allows us to do is say, okay, out of these two, which one do we have less moles of? Because that's going to be the limiting reagent, right? So we are going to lose 0.00106. It will react with this, so we are going to lose 0.00106. And that will give our final concentrations. Well, what is the concentration of this guy? 0 and 0.0025 minus 0.00106. 0.00144. Now that's the number of moles. So if we want the pH, we can't just use the number of moles. We need to do what to that? We need to figure out the molarity. So we have 0.00144 moles. What is our new volume in liters? There we go, 0.035. And we put it in there. 0.00144 divided by 0.035. The hydrogen ion concentration now is equal to 0.0411. And again, I'm always just going to keep that in my calculator and then take the negative log of it. And we get 1.39. Actually, we do have that extra significant digit there. So that would actually give us 3 there. So we can actually change that and we could actually be a little more specific on this, I believe.
Where did that 0.035 come from?
That is the 10 milliliters of the base plus the 25 milliliters of the acid. That changes our volume of the solution.
I thought that the answer was the change in the pH, not the
Yeah,
actual.
so I've
pH.
got the actual pH now, Elizabeth, and I was just getting ready to get what the change of the pH is.
Oh, okay. Sorry, you
No
circled
worries,
it.
no
Thought you were
worries at
done.
all. So what are we going to do to get that change? We need to take this and subtract the 1 from it. And that's kind of a secondary question. So we've calculated the pH of this. The change is kind of a secondary question. So we're going to subtract the 1 from that, and we're going to get 0.386. We clear on the 35 milliliters?
Yeah, thank you.
You're welcome. So another common question for this is, where would you reach equivalent points? And then you could use your MA VA over CA equals MBVB over CB. Or you might get something like this, and I think that we're actually going to reach the equivalent right here. Calculate the pH of 25 milliliters of this, so no problem there. We've already done that, 0.0025. But we have a different volume of base. So we'll take that, 0.0235 liters. Every 1 liter is 0.106 moles. 0.0235 times 0.10. And for that, we get 0.0025. So which of these is the limiting reagent? Both, right? So we're going to put point minus that. We're going to get 0 and 0. And here's a huge thing. These are strong. Can this NaCl act as an acid or base? No. Right? This is a neutral salt. It is the anion of a strong acid and the cation of a strong base. So that makes this a neutral salt. So this is not going to have any effect on this. So we will have basically, again, 1 times 10 to the negative 14th. All of it is H2O. So if we look at this, what would the pH be if we've canceled out both the acid and the base? We will
7.
get pH 7. Basically, we have the self-ionization of water occurring and stuff like that. But if these cancel out, that is our equivalence point for the strong acid, strong base, pH 7. If this were a weak acid, then this could act as a base. So at the equivalence point, that would actually bring up the pH from 7 up to higher, with that acting as a base.
And how would we calculate that?
That's going to be Tuesday's lesson.
Okay.
Yep. We said today we'd get strong acid base titration out of the way. On Tuesday, we'll do weak. So now it says calculate the pH of the 25 milliliter sample of 0.1. So we are used to this sample now. Asking the good questions, Monk. It's always fun whenever, you're asking the questions for the next lecture. And we need to figure out what the number of moles of this is. So moles of the hydroxide. Zero 0.00318. So what is our limiting reagent here? HCl. So we're going to subtract 0.0025. And we get 0 of this. We get, big number there, 6.8 times 10 to the negative 4th. Well, what is this 6.8 times 10 to the negative 4th? This is what ion? OH. That is the moles of the OH. So in order to find the concentration, I need to now take it and divide it by what? Good. The new concentration, Gabe. So we need to add 30 milliliters and 25 milliliters. So 0.0550 liters. And we get 0.01236 molar OH negative. What can we do with this? Find the POH. We take the negative log of it. And that equals 1.9 1.908 3 but it should have 3. Oh no, wait, it's a subtraction. So yeah, actually it is not 1.908, it's 1.91. Because we have the subtraction there, that's gonna make that 2 significant digits. So 1.91, and they don't want the POH. What do they want? pH. So what do we have to do to this?
Subtract 7.
Nope.
14.
There we
Sorry.
go. No worries. And we get a pH of 12.1. 12.09. Sorry. Subtraction again. So 12.09. Does that make sense? Well, we had more base than at equivalence points. So it makes sense that our pH goes up beyond 7 because we more have a higher concentration of hydroxide ions.
And how do
Cut out, Monk. You cut out, Monk. I couldn't hear that. All right. So let's take a look at this titration curve. This is a strong acid and strong base, just like we did. So if we take a look, we can make some correlations with these 3 trials here. At the beginning, we're starting off with a pH of about what? 1. We have a strong acid being titrated with a strong base. These are some things we can figure out. What else? What's our initial concentration of HCl? Right? Right up here. So that means we could find the pH of this.
well,
Pretty
just
quickly
one,
there.
right? Here's the graph.
Yeah, the pH is 1. Yep. The concentration of it is 0.1. I don't need these right here. I'm going to actually get rid of these and put molar on it. Where is the equivalence point?
At about 23 milliliters of NaOH added.
Okay, very good. So about 23. And I think we said 23.5 was the math that we calculated. But yeah, right, reading the graph, 23 milliliters of base was required to reach equivalence. What is the pH at the equivalence point?
7.
7, right? Boom, boom.
Is the pH equivalence point always going to be 7?
Strong acid, strong base, yes. And that's exactly what Hayden was talking about a few minutes ago, because our next one is going to be like the one that we did the laboratory of. So if you take a look, our equivalence point here is actually this 10, pH of 10. And that's what we're going to start talking about on Tuesday. But let's make sure we hash out the rest of this strong acid, strong base one. We got that. We got that. We got that. Another thing we could do is by looking at HCl and NaOH, we could come up with what? And this is an arrow that goes forward because, yeah, this is a neutralization reaction. We can come up with the balanced equation. Oh, so we want to take from that. Ah. How could you determine the sodium hydroxide ion concentration? Like what the concentration of this base is? You could, yeah. Another way to do it is if we know the equivalence point, right? We can use it's very similar to we use this for your laboratory. And then so we have the balanced equation. So the coefficients are both 1, so theirs are going to cancel out. We know the molarity and the volume of the acid. 25.0 milliliters times 0. Let me put it this way so no confusion occurs. Molar times the 25 milliliters. That equals the molarity of the base, which we don't know, but we do know that it took 23.5 milliliters. So we divide both of these sides by 23.5 milliliters. 0.1 times 25 divided by 23.5. Oh, 0.1. And there's where that 0.106 came from that we were using the math from before. But that's about it for strong acid, strong base titration curve. Let me see if there's anything else on here that we missed. The base is being added to acid. Reaction is represented by this. Got it. Got it. The strong, the acid is strong. We know this. 100% ionization. pH at equivalent 7. Volume of the base. Star got us that. This is the you could take what we know about the milliliters required to reach 0.0025. Basically, if you know the acid concentration, you would be able to sit there and figure out how many moles of the base would need to be reach equivalence. And then we used Malva over Ka to figure out the concentration of the base. All right. Cool. I think then what we'll do is we'll end this. You guys are gonna come in and take it or whatever. Up to you entirely. I was actually thinking about maybe taking tomorrow off if I don't get my stamina back or whatnot. But you guys have that 9 weeks assessment on there. You're more than welcome to do it tomorrow, Monday, however you choose. As always, totally up to you. And then on Tuesday, we'll meet back and we will do the week acid, strong, base titration. And the graph for that has a little bit more stuff on it. And then we'll do the question that Monk had is, how do we find that change in pH? And basically all it is we've got to use an equilibrium of how much of the salt's going to react. So it's going to be an ice table. So basically it's like a BAC table, then an ice table. Yay, tables. That's all I got for you guys. Have a great day. If you have questions, by all means, stick around. You guys there? I'm gonna boot you out so I can put this recording on there. If you have questions, speak up now.
Oh, thank you.
You're welcome. Have a good day. Dylan, are you sleeping?